Hey everyone, welcome back to my channel and another new video where we are continuing the highly anticipated data structures and algorithms bootcamp. If you don't already know, we are running a complete zero to FANG interview preparation bootcamp. So the idea is that just via watching this playlist, you should be able to clear FANG interviews like this. So we're changing the narrative, we're making people realize how easy it is to clear FANG interviews. Now, this video is very important. So there are a number of reasons. I don't want you to skip the introduction part because I'm going to tell you some important points. So few important points that I want to tell you is that today we're starting with tree data structure. Okay, the first point that I want you to remember, always remember this. When you're going for your interviews, be that for your internship interview, your Google, software engineer interviews, or Amazon or Microsoft or Facebook or any other company, your online QA rounds, those are there as well. Whenever you're doing these coding rounds, whenever you're going to your interviews, tree data structure is the most important topic. There is no other topic in the whole data structure ecosystem that is more important than tree when it comes to interview preparation. If you have your interview, the number one most important topic is tree data structure. Below that, you can have dynamic programming or linked list and other things like that. Those are also important, but nothing in data structure algorithms interviews is as important as tree data structure. Hence, this is one of the most important videos and the playlist. So by the way, I'll create a separate playlist for trees. So that's point number one. Okay. Point number two, tree data structure interview problems that you get in Google, Facebook, Amazon, or whatever, all the popular interview questions of trees. Second point I want you to realize is, please realize this right now, and I will prove it later on. These interview questions are a joke. These should be laughable. So after watching my tree playlist, when you go to your Google interview or your Facebook interview and they give you a tree question, what should be the first thought in your mind? The first thought in your mind should be laughter. Is this a Google question? This is actually a joke. Kunal proved this to us. These questions are a joke. I have proved this. I'm not just saying this. I have proved this for other data structures and other concepts like recursion, like linked list. Linked list, you may have seen a popular meme on social media, like reversing a linked list and things like that. That was like a really big popular meme, like, oh, so difficult. They're asking these questions in interviews. After watching my just 2 linked list videos, I've made only 2 videos. You can solve any linked list problems, and questions like reversing a linked list and all these other things are like, this is actually a joke. Why are people making memes about this? I can't relate to these memes. These are actually joke questions. Same thing happens with trees. Anyone who tells you tree data structure questions in the interviews are really difficult, they are just trying to sell their courses and make money. This is the most, for lack of better words, I'm trying to be like as civil as possible. It is one of the most easiest topics, but also most important. And how is it easy? That's point number 3. My playlist. I'm going to teach you the tips and tricks and the patterns to use and when to use, what type of tree algorithms, what sort of questions the interviewer is going to ask you. I will teach you that. How to think, how to apply which algorithm to which particular problem. I will teach you that. I'm not going to make 100 videos solving 100 questions. I will just teach you how to solve 20-30 questions and you will be able to solve any tree question on your own. Because the idea for me is not to make you memorize the solutions, but to build the intuition. So when you look at a question, you'll be like, oh, that's the type of the question. Kunal mentioned that if this thing is asked in this type of question and if this type of data is given, apply, these traversals or that traversals. So that's point number 3 that I want you to remember. Dynamic programming, I can say, yeah. In dynamic programming, I will not tell you that dynamic programming is a joke. Dynamic programming is can be a little bit challenging and a little bit difficult. A lot of practice and stuff is required. But things like tree and linked list and heaps and stuff like that, these are a joke when it comes to interviews. Absolute joke. Nothing good I have to say about this in terms of it's really difficult or the questions are really challenging. No. I will prove this in this video as well. Hard questions of trees will do like this. Same thing we did with recursion and linked list and all the other things like object-oriented programming and everything. So without further ado, let's talk about the prerequisites of this video. What are the prerequisites of learning trees? So the most important prerequisites when learning trees, there's actually 2. Okay, the main ones. The first one is recursion. So if we talk about the prerequisites, the first one is recursion. I have done a complete playlist on this already. It's the best playlist in the world. Not my words, it's the words of other people. So you can watch recursion playlist, and it's very important. Ideally, I recommend watching the entire DSA bootcamp that I have done from the start, so that you are in the flow and you're learning while on the go. And the point number 2 is not as important, but still important, but less important than recursion. This point number 2 will help you understand how the internals of the tree are working. So that is object-oriented programming. Again, the playlist has been covered. Okay, so these are the prerequisites. Object-oriented programming, I've covered an excellent playlist. It will help you in your interviews, object-oriented interviews and stuff like that. One thing you may be confused about, you're like, Kunal, when you were teaching recursion, you told in your recursion video that recursion is the most important topic for interviews. Now, why are you saying that tree is the most important topic? You are, contradicting yourself. So actually, recursion and trees are the same topics. It's not different. That is why both of those are important. It's not like recursion is something different, tree is something different. No. You need recursion in order to solve tree problems. Without recursion, you can't solve tree problems in interviews. Okay, so recursion is a prerequisite for trees. If tree is the most important topic, automatically recursion is also the most important topic. Okay, but when you talk about data structures, recursion is an algorithm. Talk about data structures, tree is the holy grail of data structures. It's the most important. It's like Bhagwan Shri Krishna. There's nothing above Bhagwan Shri Krishna. So trees data structure is the is the Bhagwan Shri Krishna of data structure algorithms. So without further ado, let's get started. Check out the playlist in the description below. Notes and everything in the description below. Code and everything is in the description below. And I'll teach you the theory. The implementation will do some amazing questions. The intuition, I'll teach you advanced data structures of trees like red and black trees, Fenwick tree, binary tree, AVL trees. Everything will be covered. Make sure you subscribe as well, share with your friends, and also join the DSA Learning in Public journey. So you can tweet your learnings with hashtag DSA with Kunal. If you just search for hashtag DSA with Kunal on Twitter, you will find thousands, hundreds of thousands of tweets of people. Maybe not hundreds of thousands, but like plenty of thousands, hopefully someday. But yeah, you can join that Learning in Public initiative. You will find thousands of tweets where people are sharing their journey. So join that initiative, Learn in Public. Let's get started. All right, so let's get started. First, as you know, my teaching style, I will actually tell you why we are doing the things that we are doing. Okay, so if you have seen the object-oriented programming playlist, you have seen the linked list playlist, right? So in linked list, what was happening? There were some nodes that were connected to each other. That is what was happening in linked list. Some nodes like this connected to each other with pointers. Okay, something like that. That was what was happening in linked list. And if you don't know linked list, if you are not understanding this diagram that I have just made, stop watching this video. You can't help yourself. Go back, watch the linked list playlist, watch the entire bootcamp, and then come back to this tree video. You don't know linked list and you're starting to watch trees. Are you playing with your career? What are you doing with your life? Don't do that. Okay? Cool. So if you're already familiar with linked list, then tree also you can imagine something similar. Now don't quote me on this. Tree and linked list, very different things, but just for the sake of the argument, how things are working. In linked list, you see there are multiple nodes like this, multiple nodes, somewhere in memory nodes are there, cool, no problem, but they are connected with each other. Okay, so this will be connected to this will be connected to this will be connected to this. Okay, so only two links between two nodes. Same thing happens in trees. Imagine a bunch of nodes like this. In linked list, one node is connected to other node only. Okay, in tree it is a little bit different. Every node is connected to two nodes like this. If some nodes is empty, then it will be connected to null. But every node has 2 points, and those will be to two nodes. These nodes can have some value 5, 3 or whatever. So this node can have an same thing as linked list. I don't even have to explain to you. In like the linked list node, we can have any type of node. You can have like the value can be integer, the value can be any complex data type like class human. You can have nodes of class human, class car, anything you want, right? Same thing over here. For simplicity, we'll just take numbers, no problem. You can have nodes of files, you can have nodes of anything. So that's it, that's tree. Simple. That's it. That is tree. One node has 2 pointers. There can be some complex stuff that we'll learn later on. Fenwick tree, binary index tree, all these other things. Don't worry. Forget about that right now. That is in another video. So it's not, I'm not even going to touch that in this video. That will be in the next video. Red and black, AVL, or I'll tell you what all these things are. Okay. In simple format, that is what tree is. Okay. Now, I will teach you how to build this entire data structure from scratch. We'll implement this entire thing, how to add in tree, how to remove. In this video itself, we will do it. But let's first talk about why we are doing this. Why would we want to do trees? Kunal, we have so many data structures. What is the point of using trees? Why would we want to use trees? And Kunal, can you maybe tell us, like when you were given a question, how do we know that tree is supposed to be used? How do we know which algorithm in tree is going to be used? So we'll cover all of that. So don't worry. Let's talk about why. So why are we using trees? So the number one reason is that you can insert items in trees, remove items, or find items, or traverse, or whatever in, or add or delete. Let's say we talk about simple stuff. You can add, you can delete, and you can find stuff in O of log n time. That is the main reason. If someone asks you why are you using trees, that's the answer. Okay, so efficiently inserting and deleting. That's the case over here. This is not the case in linked list, right? This is not the case in linked list. So you don't have to, like if you talk about binary search tree, so there are 3 things I'll cover in this video: trees, binary trees, and binary search trees. So if you're trying to sort, like if you're trying to store data in like partial sorted manner or whatever, but you don't want to sort the entire thing, you can maybe use a tree or binary search tree or whatever like that. We'll cover that in detail as well. So that's number one. For simplicity, yeah, add, remove, find in log n time. Okay, no problem. Now another reason is that the way in which the elements are stored in binary trees, they are very ordered. Okay, so ideally if we talk about binary search tree, then if you have one node in binary search tree, all the nodes on the left will be smaller than that, all the nodes in the right will be larger than that. This makes it easy for people to find less items, or greater item, or just search for items, or add items, delete items. That's one of the reasons. So ideally if we talk about binary search tree, we'll cover this in detail. Any node in binary search tree, if this is like 6, then here you can only have items less than 6. So like maybe 5. Here you can have more than 6 in value. So in value comparison, on the left hand side will be all smaller than 6. Similarly for 5, anything on the left hand side of 5 will be smaller than 5. So like 2 and greater than 5 but smaller than 6. So we'll have something like, you can have anything you want, 5.5 or whatever. Right? Sounds good. So we'll talk about that later. Don't worry about it right now. We'll talk about binary search trees, and that's point number 2. The ordered insertion and deletion. Okay, so that's another one. The another one is that it's cost efficient. So for example, in binary tree, you are adding so much data. So many nodes you're adding, and then so many nodes you're removing. It's like dynamic in nature. It will automatically adapt because of these constraints. Okay, so binary tree, it's not going to be like, oh, I have just inserted 10,000 elements. Now I have to restructure myself in order to be more efficient. So that restructuring thing is not required. Okay, I'll talk more about that, how that happens, but just to give you an understanding. All right, so yeah, cost efficient, and some of the tree operations that are there. So systems that are less memory efficient, you can use binary trees for that. All right, the one more thing I want to mention is that Kunal, you are saying that you can either have a left child or a right child or no children. Okay, no problem. So maybe you can have something like this. Kunal, maybe you can have something like this. One child here, one child here. No problem. Then maybe you can have no children here, one child here. Similarly, no children here, one child here. No children here, one child here. No children here, one child here. Right? You can have this like long chain. Then you'll be like, Kunal, now if you want to search, let's say you had just elements like this, just like this. Is this a binary tree? Absolutely yes. This is a binary tree. Why? Because every node has either 0, 1 or 2 children. That's true. Every node here has only one child. So it is a binary tree. The left hand side children are just null. No problem. These are just null. So now you're like, Kunal, if you want to search an item, let's say you want to search this item. Then how is this log n? This is actually n. In order to search for the items, you have to traverse n times. And you said if you want to insert an item maybe over here, then it will be again traversing n times. It will check for this one, then this one, then this one, then this one, then this one, this one. But Kunal, you said that the benefit of binary tree is that you can add, insert and search for items in log n time. Then how are you doing it in n time and you're calling this like, why are we using binary search tree now? You know, what are the benefits? So the thing is that this is the limitation. This is the limitation of binary, that this thing is called a what? Unbalanced binary tree. Unbalanced binary tree. Let me give you an example. So for example, if you talk about binary search tree, I'm just giving you a hint right now. Left hand side smaller, right hand side bigger. That's it. So let's say your main node over here is 10. Like this. Now you're like, hey Kunal, please insert 5 in this node. Okay, so 5 is greater than 10 or less than 10? 5 is less than 10. So where will it go? Left child or right child? Left child. Because all smaller items go on left. Kunal, please insert 20. Okay, so I'll start from here, always start from here, and I'll be like, okay, 20 is greater than 10. Okay, 20 will go here. Kunal, please insert 7. Okay, 7 is smaller than 10 or less than smaller than 10 or greater than 10? Smaller than 10. Okay, it will go in the left hand side. 7 is smaller than 5 or greater than 5? Greater than 5. It will go over here. No problem. Kunal, please insert 18. 18 is smaller than 10 or greater than 10? Greater than 10. Right hand side. 18 is smaller than 20, greater than 20. Smaller than 20, left hand side. Like this. So that's how you're inserting in binary search trees. We'll cover this in later on. But imagine you're again inserting in binary search tree and you're saying, Kunal, please insert again, let's say insert 10. Okay. Kunal, please insert 15. Left or right? Right. Kunal, please insert 20. Okay, 20 is greater than 10, so left. Greater than 15, again left. Sorry, greater than 10, right. Greater than 15, again right. Kunal, please insert 22. Okay, greater than 10, right. Greater than 15, again right. Greater than 20, again right. Kunal, please insert 30. Kunal, please insert 40. Kunal, please insert 45. Kunal, please insert, it's like 100 items like this. Now if you want to find an item, you say, Kunal, okay, try to find 45. Okay, search for this, go right, go right, go right, go right, go right. So you search for n times. It became O of n, which is not something we need with binary trees. The worst case should be log of n. This is what is known as a unbalanced binary tree. So if you have an unbalanced binary tree, your time complexity will be O of n and everything that you have worked for will be gone to waste. How do we solve this problem? How do we solve this problem? How to solve this problem? How to solve? How to make sure that the trees remain balanced all the time? We'll also talk about what balanced means. Balanced basically means like at any point of time, the difference in height should be around like, 1 plus 1 minus 1, 0 or something like that. We'll cover that later. Okay, so here you can see difference in height if this is level 1, level 2, level 3, level 4. So you can see any between two, like between these two, if we talk about, say this one, and this one, 1, 2, 3. There's a 3 difference. Unbalanced. Unbalanced. So that's how you figure out whether it's not. So how to solve this problem? Okay, you can set your own factor to it, like 1 minus 1 or whatever. We'll talk about that later. But how to solve this problem? Create binary trees that will balance themselves automatically. These are known as self-balancing binary tree. Self-balance binary tree. This is future video, advanced concept. Next video. Okay, but I just want to make you understand what are the limitations of trees. If you don't have a balanced binary tree, then it will cause you problems. What are the problems? O of n time complexity. How to solve? Self-balancing binary like AVL and stuff like that. Next lecture. Okay, we'll cover that in detail. So that was one of the limitations. Okay. Also, one other limitations is that it's inefficient for sorted data. Okay, if you're working with sorted data or whatever, binary can be a little inefficient. So that's also one more thing to consider. Okay, let's move forward. Last part of the theory, then we move forward like with more advanced stuff. Okay, one more point in theory I want to discuss is where is it used? Kunal, you're talking about binary trees. Are there any real world applications that use binary tree? Bro, it's used so many places. Okay, file systems. So binary trees are used to represent file systems, you know, your folders and stuff like that. You can use that. And when we talk about the nodes, you know, the nodes, every single node can represent a folder, directory, or like a file with the parent-child relationships and things like that. Okay, so file systems, that is where binary trees are used. Databases. So when we talk about like the AVL stuff, because you have fast retrieval of data, so in databases many times binary trees are used. The next one is in network routing. So you know, routing the network calls and everything. I've covered a complete 4-hour long course on networking. I've mentioned this there as well, like how the pathfinding algorithms and stuff are used. So over there also it's used. Pathfinding algorithms, over there also binary stars is used. Algorithms, networking. Okay, so in networking binary trees are used. Where else binary trees are used? Binary trees are used to solve complex mathematical problems, and these are the mathematical equations can be represented in the form of a binary tree. I will teach you this as well. There are 3 traversals we will learn in this video. One of those traversals is going to be used in solving mathematical problems. So that's going to be pretty cool. Maths, right? Decision trees, those are another, you know, pretty nice machine learning algorithms. I love teaching machine learning. I'm so excited to teach you all machine learning. So decision trees, machine learning algorithm, machine learning, very popular. So in decision trees it's used as well. One project that we'll do on binary trees is compressing images, compressing files, Huffman coding. So compression of files, binaries are used in that, right? One more thing is that another data structure that we'll be using are the binary trees will help you in future data structures. So future data structures also use binary trees. Data structures, like what? Like heaps. Binary heap, you may have heard, heap is popular. In heaps, binary trees are used. Graph trees are used. Tree is actually a graph. Okay, so this is actually, we're doing graphs right now. Tree is a type of a graph. Graph we'll do at the very end after dynamic programming. But tree is actually a type of graph. It is directed acyclic graph. It's directed. Acyclic means no cycles. Graph, right? I'm really excited to teach you graphs. So yeah, it's a type of graph. So in graph theory also you have trees. Though that's it. Just I mean, the use cases are much more than these points, but just to give you an idea, you can Google yourself where are trees used or whatever, and you will find many examples and many case studies on that. All right, now let's talk about trees itself. Let's talk about trees. Let's talk about binary trees, binary search trees. Let's talk about how it works, how to add. Let's talk about complexity. Let's talk about some code. Let's talk about the implementation, how to implement these trees in Java. I will teach you theory as well and the thought process. So it does not matter if you're using Java, Python, C++, whatever. You can code it in whatever language you like. I'll use Java because we've been using Java for so long. I like how Java is like really, there's so much control over the language, so like so many things you have to write and everything, so it's much more clearer. Let's get started. Okay, now let's learn a little bit more about what are the properties of binary trees and how it is structured. So we're talking about the structure now. So I'll talk to you about binary trees. We'll implement these. We'll see what the properties are. We'll code it and see some functions and all the stuff from scratch. We'll do everything. And then I'll talk to you also about binary search trees, because it's important to learn about the basics also. And then we'll talk about binary search trees. Then in future videos in the next, we'll talk about self-balancing trees like AVL, red and black and all these things. Okay, so if I talk about tree, then I already told you that, there's one node like this. Let's say it has some value. It is pointing to two other nodes and whatever. Forget about the left being smaller, right being bigger, right? We don't have to talk about that. That's binary search tree. We'll talk about that property later on. For example, right now you can just imagine that left and right, it doesn't have any rule that, okay, left has to be smaller, right has to be bigger. No, we can insert it however we want. That is binary tree. And where we have to have the rules like left is smaller, right is bigger, that is binary search tree. So that is coming after this concept. So one node and it having two nodes and everything. So how it is structured basically is that a node is basically, like we already talked about, it's type of a data structure. And like in linked list, we had one node pointing to other node. So in linked list, we had, if you have seen the linked list one, so we had a type of node. What does it have? It has an int value and it has a node type that is pointing to next, which is the next one. That is for linked list. In binary tree, same thing we have a node, and that node type is going to have three things: int value in this example, node left, and node right. Very simple. If you have done linked list, this should be pretty easy for you to understand. It just has two pointers. That's it. Two things is pointing to. And these individual circles or boxes can be anywhere in the memory. But the important thing is every circle is pointing to another circle. Two circles. Those two circles pointing to other two circles. So it's not like array, which is the data is like sequential. Okay. Same thing as linked list. Okay. Theory wise and intuition wise, how it's working is like linked list. In linked list, it's pointing to one. Here it's pointing to two. That's it. If you have done linked list, you will be able to understand this. All right. So you can either have two nodes or you can either leave it empty also. Stuff like that. All right. Now, the size of now let's talk about some of the properties. Then the first property we're talking about, what is the size of a tree? Properties. When we talk about the size is equal to total number of nodes. Total number of circles that you can count. No need to explain. Very simple. The second one is child and parent. So the child basically means if two nodes or any node, it's very, very simple, very straightforward. For if I add some numbers here, 6, 8, 9, 10, 3, 4, if I talk about 14, then 14 is a child of 6. 9 and 11 are children of 8. That's basically what a child-parent relationship is. Siblings. If any two of the nodes have a similar parent, they are siblings. They are siblings. These are very simple concepts. These are siblings. If any two nodes have, so we talked about child and parent, talked about siblings. Edge. Edge basically means the line that is connecting two. So this is an edge. Two nodes being connected by a line, that is called edge. And then you have the height. Height basically means number of edges between two nodes. That's the height. Okay. And not just the number of edges, maximum number of edges. So the idea here is maximum number of edges. If I add something like 15, So what is the height of 15? The number of edges between 15 and the topmost is 1, 2, 3, 4. Height is 4. Okay? Sounds good? If you talk about 3, what is the height of 3? So the height of 3 is, start counting down from bottom to up. That's actually what the height basically really means. So height basically means what? How above it is from the lower ground. So the lowest node that you have, okay, lowest leaf nodes, by the way, these are called leaf nodes. So these are called leaf nodes. Leaf, 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 leaf. That's another term we learned right now. I know height might be a little confusing. I will tell you right now. Leaf nodes. So leaf nodes are basically like the bottom nodes or whatever. Height basically means, if I write it down in a simpler format, max number of edges from the node you are trying to find the height, from the node and leaf node, that is known as height. From that node to the leaf nodes. So if you try to find the height of 5, so what are the number of edges from 5 to leaf nodes? So the number one edge is 1, 2. There is 2. What else? 1, 2, 3, 4. What else? 1, 2. What else? 1, 2, 3. What is the maximum of this? 4. Then the height of 5 is 4. What is the height of 8? Height of 8 is 1, 2, 3 or 1 or 1, 2. So what is the maximum of 1, 2 and 3? 3. So this is the height, 3. From that node to the leaf node, the maximum of that is the height. Okay? Sounds good? Very easy. Let's move forward. Apart from that, there's one more thing called level. What do you mean by level? So level basically means the difference of height between that node and the root node. So height is what? Height basically is top to bottom. From that node, you check out what is the lowest you can go, what is the leafest you can go, where is the bottom leaf. But for level, it is the height difference between that node. Okay, calculate the height of that node, calculate the height of the root node, subtract it. That's basically what the level is. So root node level is always 0. So subtract height of root minus height of node, and the height difference. So node root height, here I can say, is equal to 0. Level 0. No, not root height, root level. Root level is equal to 0. Why? Because subtract height of root minus height of node. So if node is equal to root, then what would this equation become? Height of root minus height of root. So level of root is what? 0. A minus A is equal to nothing, 0, right? So that's basically what it is. And one more thing is, if I talk about level, so this will be level 0. This is what? Level 1, because height of node, which is 1, 2, 3, 4, 1, 2, 3, 4 minus height of this 1, 2, 3. So 4 minus 3, 1, 1. Okay. And after that you have ancestor and descendant. So if there is a path that you can find from A to B, then A is the ancestor of B and Y is the descendant. Same thing that happens in our human life. So if you find a path like this, if you find a path from 8 to 4, then 8 is the ancestor of 4, grandfather, great grandfather or whatever. That is very simple if you imagine it as like a family tree. Okay, those are some of the properties. Ancestor and descendant. Alright, sounds good. Okay, let's move forward. Now let's talk about types of binary tree that we have. So types of binary tree. So the first is called a complete binary tree. Complete binary tree. What is a complete binary tree? So in a complete binary tree, all the levels that we have, we talked about levels right now, they are filled apart from the last level. Okay, apart from the last level. But I'm not going to write it down, so you can make your own notes. All the levels are full apart from the last level, but the last level is full from left to right. So for example, all the levels are full. Okay, here all the levels are full. You can't say something like this is another level, so you can't say something like this. No, because this level number 2 is not full. Every level has to be full. That's case number 1. Last level may not be full, it's okay. But last level, when you're filling, it should be full from left to right. So this is not a complete binary tree because you missed out on this one. So you want to fill it, you will fill it from left to right. That is complete binary tree. I'll write it down, no problem. All level full, last full from left to right. That is complete binary tree. Moving on. The next one is called a full binary tree or a strict binary tree. So I keep looking over there that my video is recording or not, because sometimes I am teaching so much on when I'm recording videos, and I check OBS, which is the tool I use to record videos, and it's like, oh, you did not click recording. So all right, now we're talking about full binary tree or strict binary tree. What is this? So full binary tree and strict binary tree, in this one, each node has either 0 children or 2 children. No 1 children. Either 0 or 2. Okay, every node, either 0 children or 2 children. No single child. So, an example, I'll write it down over here. Either 0 or 2 children. So, example, something like this. This node has 2 children, correct. This node has 0, okay. This node has again 2. This node again has 2. This is a full or strict binary tree. Now it is not, because this node has 1 child. No, not possible. Everyone has to have 2 or 0. Siblings or nothing. Okay, third type of binary tree. And this is actually used, like the use case of this is in compression. We will use this in compression. Okay, in Huffman coding and stuff like that. And there's one more tree we'll learn, segment trees. Very important for comparative programming, not for data structure, like interview preparation. Okay, point number 3, we have the perfect binary tree. We say nothing is perfect in this life apart from perfect binary tree, because it has in its name perfect. So all the internal nodes have 2 children and all the leaf nodes are on the same level. Okay, so all the levels in a complete tree, they are filled like as much as they can have, and that's it. All levels are filled. So basically all levels are full. Example, fill every level. All the leaf node should be, so if you add one here, then you have to add it for everyone. That is perfect binary tree. Okay, very simple, right? Cool. Apart from that, there's another one. This one is called height balanced binary tree. So when the height of the binary tree, we already talked about the height, I just told you. When that is O of log n, it is called height balanced, where n is the number of nodes. So for example, AVL and red and black trees that we'll learn later on, these are the average height that we have, that is O of n, O of log n. Height balanced. Average height O of log n. Okay. Next one we have is a fifth type of tree, skewed binary tree. What is skewed binary tree? In skewed binary tree, every node has only one child. Every node has only one child. Okay, so what is the maximum height, average height? O of n. O of n. Like linked list. This is like linked list. This is not cool. Very bad. Okay, that is skewed binary tree. There's one more, sixth one, called ordered binary tree. What is ordered binary tree? Ordered binary tree is in which every node follows some property. Okay, every node has some property or conditions, has some property that it follows. You already know an example for this. Example, binary search tree. Every node has a property in binary search tree. What is that property? I just told you. Left should be smaller, right should be bigger. Okay, cool. Sound good? So this was types of binary trees. Okay, I will tell you some of the properties that will help you in questions. Let's talk about some properties. Properties that will help you in some questions. Let's talk about properties. We'll also code, don't worry, I'm not going to skip anything. So property number one. Property number one is that the total number of nodes in a perfect binary tree of height h. If we talk about the perfect binary tree, which is which one? This one, all levels are full. So in a perfect binary tree, height is equal to h. Let's say the total number of nodes, total nodes is equal to what? Total number of nodes is equal to 2 raised to the power height plus 1 minus 1. Okay, and also since every level is full, then perfect binary tree is the tree that has the maximum number of nodes. Okay, sounds good. Kunal, how is this possible? Like, how did you come with this formula? Think about it. Every node at that level, number of node at each level is equal to what over here? Number of node at every level. Here we have what? 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. Next you will have what? 16, because every single one will be 2. So it will keep on doubling. So it's keep on doubling. It's very simple. Mathematics, simple mathematics, high school mathematics. At every node, it is doubling. So I can say that if at every node, at every level it is doubling in number of nodes. Level 1 will have one node, level 2 will have two nodes, level 0 actually, this is level 0. Level 0 has one node, level 1, which is level 1, has two nodes, level 2 has four nodes, level 3 has double of 4, which is 8 nodes, level 4 will have double of 8, 16 nodes, level 5 will have double of 16, which is what, 32 nodes. So if level is equal to I, then number of nodes on that level is equal to what, 2 raised to power I or not? Very simple. 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, 2 raised to power 4, and these powers are what? Levels. It's very simple. Okay. Now, if we talk about total number of nodes, then to 2 raised to power 0 plus 2 raised to power 1 plus 2 raised to power 2 plus 2 raised to power 3 plus so on and so forth. Till which height? Till height, let's say if you have h, 2 raised to power h. So this will come out to be equal to what? This is what? This is geometric progression. If you have studied for JEE, this is very basic. What is the formula for geometric progression for this sum? 2 raised to power height plus 1 minus 1. That is the total number of nodes. Okay, property 1 clear? Alright, moving on. Property number 2. Property number 2 is that if we talk about perfect binary tree, then the total number of leaf nodes in a perfect binary is equal to what? We already spoke about this. Total number of leaf nodes will be equal to what? If height is h, then at every level we have 2 raised to power the level. So 2 raised to power height. That's it. Total number of leaf nodes, 2 raised to power height. Leaf nodes in perfect binary tree is equal to 2 raised to power height. Okay. Sounds good. So if we talk about, like, if the number of leaves, the number of leaf nodes are 2 raised to power h. Okay. Now similarly you can calculate what are the number of internal nodes apart from the leaf. So total nodes 2 raised to power h plus 1 minus 2 raised to power h. Okay, this is equal to what? This is equal to 2 raised to power h minus 1. Sounds good? Simple stuff, very easy. Okay, I'll share some other properties. So if you have n number of leaves in a binary tree, then how many minimum levels, at least levels that you will have? Let's say n is equal to the number of leaves, then what is the at least how many levels you will have? You will have log of n plus 1 levels at least. So again, very simple. You can use the same formula that I did previously to decode this. Okay, and similarly if you have n number of nodes, in that case the minimum possible height or the minimum number of levels will be equal to what? If you have n nodes and you're distributing it like that, how did we calculate the height? This is sort of similar like the formula in binary search. You can draw it and you can figure it out if you want to prove it, but the answer for that is log of n plus 1 minimum levels you will have. So another property. Okay, property number 4. Property number 4 says that if we have a strict binary tree, what is a strict binary tree? Where we have a strict binary tree, this one, either 0 or 2 children. So if we have a strict binary tree, then let's say n leaf nodes. Strict binary tree, total leaf nodes is equal to n. You have n leaf nodes. Then the number of internal nodes are going to be equal to how much? You have n leaf nodes, then how many internal nodes will you have apart from the leaf nodes? How much? N minus 1. I'll prove this as well. Internal nodes. Okay. So we can also say that the number of leaf nodes is going to be equal to what? Internal nodes plus 1 in a strict binary tree. Okay, sounds good. So how is this true? Let's see how this is true. For this you can use like induction. You can check out Mathematics for Computer Science MIT OpenCourseWare if you want to learn more about proofs in mathematics. But there's a famous proof in induction. Let's say we have a node, a perfect tree like this. Sorry, not a perfect tree. It's a strict tree. 0 or 2 children. Okay, internal nodes here is equal to what? Internal nodes equal to, I'll add 2 more here. So leaf nodes are, I'll put leaf nodes in blue. Leaf node, leaf node, leaf node, and internal nodes are black. Leaf node equal to 3, internal node 1, 2, 3, 4. 4. Let's say you add an item. So you cannot add one node. You can only add 2 children or 0 because it's strict. So let's say I add in 2. Here. Now see what happened. This does not become a leaf node anymore. So leaf node was reduced by 1, internal was increased by 1. Okay. But you got 2 more leaf nodes. So added 2 more leaf nodes. So in reality, this equal to 3 plus 1. So it increased by 1. Leaf node increased by 1 and internal node increased by 1. Okay. So in any situation, this will be true in any situation. That's the thing, right? Because both of these have increased by the same number. Hence, this formula is going to be still valid. You can't say, oh, leaf nodes increased by 2, internal nodes increased by 1. Then now leaf nodes are increasing more than internal nodes. No, they are increasing the same way. So plus 1 cancel each other out. Formula holds true. That's proof by induction. Hope that was clear. It was very simple. Okay, sounds good. Let's move forward. So one more thing I want to mention in properties, we'll do it in graphs, but since tree is a graph, it's called degree. So degree is basically the number of edges or the number of, in simple terms, children you have. So 5 has a degree of 2, 6 has a degree of 1, 8 has a degree of 2, and leaf, which is 15, has a degree of 0. And the degree of the tree is the maximum degree you have. So at max, your degree can be 2 only. So degree is either 0, 1 or 2. Alright, cool. Another property, which is property number, let's say 5. It's very simple. The number of leaf nodes is always going to be equal to 1 plus number of internal nodes with 2 children. The proof of this you can look on yourself, like it's a big proof, and I think it's like beyond the scope of this video, because otherwise this would be a mathematical proof video and not a leaf video. So if you want, you can Google it, but an example of this, number of leaf nodes. Here number of leaf nodes in the above example is equal to what? 4. It should be equal to 1 plus number of internal nodes with 2 children. How many nodes we have apart from the leaf nodes in this above diagram that have 2 children? We have 1 because this has 2 children, 2, this has 2 children, 3, this has 2 children. Apart from the root node, that's also one more thing. Not including root. So total we have 3. So this is true. Sounds good? Number of internal nodes. So root itself is not like an internal node. That's why I had to mention it specifically, like, okay, fine, to remove confusion, but that's it. Okay, pretty cool. Okay, now let's talk about the implementation of binary. Let's look at some code and implement it and see it in working and how it works. So there are 2 ways by which you can do this. Okay, if we talk about the implementation, let me just put it in a new page. So let's talk about the implementation. You can do it in 2 ways. Way number 1 is using your, like your pointers or whatever, and it's like a linked representation. So linked representation. So in memory it's like this, and just like you're linking it together, like you have objects, and same like linked list, linked representation. Okay, that's very simple. That's what we will do in this video. And the next one is sequential. This is using an array. Now the problem here is you have to define the size of the array or whatever. So what you can do is, let's say we have a tree like this, 5, 6, 8, 9, null, 11. So level wise you can have indices 0, 1, 2, 3, 4, 5, and in the array index 0, 1, 2, 3, 4, 5, 6. 0 will be 5, 1 will be 6, 2 will be 8, 3 will be index 3 have 4, 4 has null, 5 has 11, so on and so forth. That is sequential representation. Okay, sounds good. So we are not going to use that because it's not very, like it's not efficient in terms of, like, you have to define the size of the array and everything. But there can be some situations, where there's like less memory overhead in like an array implementation. That example can be of when we do an implementation of a heap, which is a complete binary tree structure. That is when we will implement trees in an array. Okay, sounds good. So that is when you'll use it. So Kunal, when will we use it sequential? Because the problem here is what? Many nodes can be null, so you can be having like memory as allocated, but you're not using it. How will you solve this problem? Well, if there are no nulls in the between or whatever, that is a complete binary tree structure. And what is the type of a complete binary tree that we'll be using? Heap. So when we implement heap, we will not use linked representation, we will use sequential. And since it's array, you can easily get the data out of it like that. Also segment tree, which is a strict binary tree. In that also we will not use linked, we will use sequential. But in normal binary search tree, left and right in between anywhere can be what? Empty. So we will use linked representation using the pointers. Okay, so if you want to see how to do trees using array, then come back to the heaps lecture that we'll do in the future after this, and segment trees, which is also something we'll do after this. So for that we will use arrays to implement trees. Hope that is clear. Okay, let's move forward. Okay, now let's talk about the implementation. Let me tell you a bit about the time complexity and everything. It's actually pretty simple. So we'll learn more about time complexity as we do questions, but it's pretty straightforward. You have a tree like this. Let's say it's like full over here and everything. Total number of nodes is equal to n. Then what is the maximum level that we have over here? Similar to binary search that we did previously, what is the maximum number of height? So here you have, let's say n, and let's say if here you have this is 1, this is 2, this is 2 raised to power 2. Similarly, you have 2 raised to power 3, 2 raised to power 4 or whatever. Keep going, 2 raised to power height or whatever. And here we have that in the end you saw that 2 raised to power height, total number of nodes, 2 raised to height plus 1 minus 1. So if I just talk about 2 raised to height plus 1 minus 1, nodes is equal to 2 raised to power height plus 1 minus 1. I'm just removing the like constants or whatever, and because that's, if you have seen the time complexity lecture, you can do that. So I can say log of n is equal to h log 2, height is equal to log of n. Simple, very simple. If you've done time complexity, this is nothing. We have covered so much complex time complexity problems. Okay, please watch the time complexity video if you have not done this already. Okay, so 2 raised to power height, whatever the height plus 1 minus 1, height plus 1 minus 1. So minus 1 will be removed. Okay, 2 it's actually into 2, plus 1, so it's into 2. That into 2 will be removed, and this is what we are left with. Now we take log on both sides, and height comes out to be log n base 2, complexity wise. So that's why if we talk about, let's say, insertion, then we talk about, let's say, how do we insert in a binary tree, not binary search tree, normal binary tree. Then we have, let's say, just insert the root node first. Okay, I will insert the root node. Now what? Now ask, do you want to insert on the left hand side of this node? Yes, I do. Okay, then insert it. Now ask, do you want to insert on the left hand side of this node? Yes, I do. Okay, insert. Do you want to insert the left hand side of this node? No, I don't. Do you want to insert the right hand side of this node? Yes, I do. Insert. Do you want to insert the left hand side of this node? No, I don't. Do you want to insert the right hand side of this node? No, I don't. Then go back. Go back. So you can see the recursion call that is happening. Left, it went into left, it went in the left, it went in the left, then it came back, then it again went in the right, then it went in the left, came back, right, came back, then it came back again, it will go in its right. Do you want to insert? Yes, I do. Sure, I'll insert it. Then again in the left. Okay, so in the insert function, it's checking the insert for left and then the insert for right. Simple. For recursion, build the tree. Okay, if you don't build the tree, you will not understand it. So it's very simple. Here I will just ask it to insert the root node. Then I will ask, do you want to insert on the left? Yes. Do you want to insert on the left of this node? So that's how it will go. So it will be something like this. Insert the root 15. Do you want to insert in the left of 15? So in the recursion stack, it's at level 15 right now. Okay, not level 15, the node 15, which is level 0. So it will go inside this recursion call. Do you want to insert in 15, left hand side of 15? Yes, I do. Okay, so I'm in 15 here. Now I'm in the left hand side of 15, which is, let's say I inserted 8. So I'm in 8 over here. Do you want to insert on the left hand side of 8? Yes, I do. So every call is going to be 2 calls, left and right. Do you want to insert on the left hand side of 8? Yes, 7. Now I'm in function call 7. Do you want to insert the left hand side of 7? No. Then do you want to insert the right hand side of 7? No. Then it will go back and it will come out of the function loop and it will be like, okay, now I'm at level 8. 7 will come out of the call stack. Do you want to insert in the right hand side of 8? Yes. Inserted 9. Do you want to insert now 9 is in the call. Do you want to insert in left and right of 9? Let's say I don't. Okay. Now 8 is, both the calls of 8 are done. So it will be removed and it will be removed from the stack. Now I'm in 15. So you get the idea, basic recursion. We have already done this stuff before. Code wise, it will look something like this. Code wise, we have, you can just make a check. Let's say do you want to insert. So that will be either true or false. So you can make a Boolean check. Let's try to code this and then it will make more sense. Then we'll debug it also, so you can see how it is working internally and how this simple recursion call is working. If you don't understand right now, it will make more sense once we have coded it. So let's code it. All right, so I'm going to create a new file here in my online editor. I'm doing this so that you can also, directly run the code, and all the links can be found in the description below. I'm going to call this one trees lecture 1, create all the code samples and everything. So you can just click on fork or something and you will be able to run it on your own system. Many people don't have like powerful laptops or whatever, so this can help you. Let's say I talk about, I'll just rename this to binary tree. Okay, so we implement it from scratch. I don't need my console here right now. I can just close it and close it as well. Okay, so what do we need? We need a node. So here we have a node. We need a node type. So I can say it will be private static class node. This will have some values, like I'll have private int value. What else does it have? It has a node left and node right. That's it. And also when you create a new node, then you have to initialize the value. So a constructor, this dot value is equal to. If you don't understand what I'm doing here, please watch the object-oriented programming playlist. This is very simple stuff. It is exactly the same thing we did in linked list. Okay, cool. So we'll use that, don't worry. That's one. And then constructor public binary tree. For now we have it like this. And what we're going to do is, for this binary tree, we're going to have one node. So I'm going to call that the root node. So similarly, you had the main node in the linked list, root. Okay, sounds good. What I'm going to do is I'm going to populate this. So now insert elements. Okay, let's insert elements. Zoom in a little bit so you can see. Right. So public, I'm going to say that we can make a populate function which is going to populate as we enter. This is not binary search tree. This is we are inserting in normal binary tree. So I can say public, it's not returning anything. Populate, it will take a scanner. Okay, and we can say system dot out dot println. What is the first thing it should ask us? Enter the root node value. Okay, so my value is going to be equal to what? I'm going to take it as an integer, scanner dot next int. Then my root is going to be equal to what? I'll create a new node with this value, that is correct. And then once my node is added, I'm going to call another recursion function that will fill the entire tree. We did something similar in like recursion. We have a main function and then we have a little helper function. So that is what we'll do. So I'm going to add in over here, I'm going to say populate, and I'm going to pass in my scanner and my root. Now I'm going to create this populate function. This will be private populate scanner node. Looks good. Now what we're going to do is populate. Right. So what we're going to do over here is that first we're going to ask it enter the left node. Yeah, it's asking me, it's already giving me suggestions, the AI. So we're not going to you can use the AI if you want, but I want to start it from write it from scratch. So print ln, I'm going to say you know, do you want to enter left of node dot value? That is what we are asking. And then you will be like boolean left is equal to scanner dot next boolean. Okay, if left is correct, in that case what we're going to do, we're going to be like enter the value of the left of this node. So after that you enter the value scanner dot next int, correct, create a node dot left is equal to node value, correct, and then call the recursion again. So what happened here was that, let's see what happened. So you run the populate function over here, it will say enter the root node. Enter the root node, it will be like it will take an integer from you, create a node out of it, it will create a node, you take an integer, it will create a node out of it like this, and then it will call, it will set that to root, and then it will populate the rest of the tree. So it will now go in this function. This is actually the recursion function. So here it's saying, do you want to enter the left of 15? I'll be like yes. So if correct, yeah, enter the left of 15. Currently the node value here is 15. So if I talk about the node value right now is going to be equal to 15. So it's going to be like enter the left of 15. Yeah, so it will create a node called node dot left, means what is node right now? 15. So 15 dot left will be the new node, whatever it is. Let's say 6. Okay, now it's going to call the recursion. Okay, now it's going to call the recursion for 6. So it's going to call the recursion, and here it's going to be like, hey, see, populate node dot left. What is node dot left? 6. So now it's going to call populate node dot left. Once it is 15, it's going to call calculate populate node dot left 6. Now you're inside this 6. It's going to be like, hey, do you want to insert the left of node dot value? What is the node dot value right now? 6. Do you want to insert left of 6? Yes, I do. So okay, print enter the value of 6. No node created new node 6, and 6 dot left is equal to new node value. 6 dot left is equal to new node value 8, for example. And then you're going to be like, okay, node dot left is equal to the populate. Now it's going to call for 8. So it's going to call for 8. Simple. Now similarly for 8 is going to be like, hey, do you want to insert the left of 8? I'll be like, okay, no, I don't want to insert the left of 8. Okay, if you don't want to insert the left of 8, then what you can do is, do you want to insert the right of 8? Right of 8, node dot right is equal to this. Then you call node dot right. So now it's going to be like, hey, do you want to insert right of 8? Do you want to insert right of 8? Sure. Okay. 10. Inserted. No problem. Now it's going to call populate for node dot right. What is node dot right? 10. It's going to call it for 10. Now for 10 again, it starts from populate. So it will start again from here, from this line. It's going to be like, hey, do you want to insert left of 10? I'll be like, no. Do you want to insert right of 10? I'll be like, no, I don't. Then function call finished. It will come out of here, and it's not going to run either this or this. It's going to come out of here. So function call finished, so it will be removed from the call stack. Now it will come out of 8. It will come out of 8 from where it was called. So it was called from here because we inserted 10. So it will come out of here. Is there anything after this? No. Then 8 function call is also over. Now it will come out of, I will be now at 6. I am now at 6. So I will come out of where? The last call that was made for 6. Last call made for 6 was towards the left, which is this one. So now we'll come out of here. Okay, now it's going to be like, hey, do you want to insert the right of node dot value, which is 6? Do you want to insert right of 6? Do I want to insert right of 6? Sure, I'll insert 14. Now it's going to call recursion call on what you have just inserted. Recursion call on what you have just inserted. 14 will go over here. Do you want to insert left of 14, right of 14? Let's say no for simplicity. Then okay, it will be removed. Then it will be like, okay, now 6, both the calls have been done. It will be removed from this line and now it will be removed. So function is over. Function is over. Now it will be in 15. It will go out from which line? It was the last call of 15 was left hand side. So it will come out of here or here. Obviously it will come out of here. Now it will be like, do you want to insert right of 15? No, I don't. Never mind. That's it. And then it will come out of here. Then it will come out of populate where it was called for the very first time. Where was populate called for node 15? Here. So it will come out of here, function over. We did it, we debugged it, we saw the structure of how it's working, how the function calls are working. Okay, that's basically how the populate works. Simple stuff, very easy, right? Okay, cool. Now what we're going to do is we're going to call the display function. So we want to also see how we can display it in a nice way. Okay, so what I'm going to do is public void display. I'm going to call another display that starts from root, and let's say we add an indentation. For that we add just a string. Okay, private display node string indent. It already knows what I want to do. This AI is really smart. Okay, it's actually suggesting the right thing. So when we want to display, how do we want to do this? So let's say we have something here, let's say called we have 9. So how do you want to display? We first display the node itself, the node we are at. Okay, system.out.println, we first display the node value. So indentation plus the node value. Indentation is just the space that we are providing. So that is going to be printed, no problem. Now what we are going to do is the base condition, if node is equal to null, if we are at, like, if there is no node, then we will just return. That's the base condition. If node is equal to null, return, don't do anything. Now the recursion call, we have displayed 15. Now what we're going to do is we're going to go to the left, we're going to display left, then we're going to display right, and every time we are displaying it, we are going to increase it. So it should be displayed something like this. First 15 is displayed, then 6 and 9 are displayed. So 6 is displayed and let's say 9 is displayed. And then we have 8 and 6 is displayed, and then so we will call left first. It will display 6, then we will display 8 as well, right, over here. Then we will display, like, okay, now we display what is in the right of 8, which is, let's say we display 10, and then for 6 again it comes out, then it comes out, it will display 14 like this. This is another level, right? And then it comes out 6, then it will be 9, so on and so forth. Okay, so let me just see. I'll just call display with node dot left. I'll run it and show you display. You'll be able to understand. Remember what I taught you in recursion. Indent plus, let's say we add a tab. Remember what I taught you in recursion. You know, how do we work with recursion? Draw it on a pen and paper, otherwise you will not understand. All right, that's done. Cool. Now what we're going to do is public static void main scanner, new scanner, tree.populate scanner, tree.display. So it did everything for me. No problem. So I just created a new scanner, passed in scanner in populate, new binary tree. Alright, actually what I'm going to do is I created a main class and I'll just call the main function in that. And let's see how it goes and let's see how it works. So I'm going to call it and I'm going to say, by the way, you can also debug it. You can use the debug pointer here and it has a debugger. So you can see over here, there's a debugger that you can use. But let's just call this, enter the root node. So let me just show you the code side by side and show you how it works. So we are over here, populate. It's saying enter the root node and now you're inserting the root node which is 15. Okay, no problem. I inserted 15. Now it's going to call the populate. It has set the root value. Now it's going to go in the populate function. Now our recursion will start. So current value is 15. Current value here in the recursion function is 15, which is in my stack. It's going to be like, hey, do you want to insert in the left of 15? I will be like, yes, I do. Enter the value. So I'll insert 6. It's going to create a new node. It's going to create a new node and insert it in the left. Now it's going to call recursion for this node, which is populate. So again, same function will be called. This is recursion. You see how it's working? Recursion node.left, which is 6. So 6 will now be over here. Now we are calling 6. Now we are calling 6. Do you want to insert? Now it will start again from here. Because you have just called populate, it will start again from here. Do you want to insert left of 6? I will be like, yes, I want to insert left of 6. I will be like, yes, and I want to insert 8. Now I have inserted 8. So it will call again the same function for 8. 8 is now again called. It is in the recursion stack. Do you want to insert? Now again it will start. Since you have called populate, so it will start again from here. Do you want to insert left of 8? Now node is 8. I will be like false. I don't. So when you insert false, from the 8, it will actually not run this thing. It will now run this thing, because if this is true, then only it is running it. Okay. If this is true, if left is true, but I will be like false. So this actually is false. This will never run. It will go over here directly. Do you want to enter the right of 8? And I'll be like, yeah, sure. I will insert true and I will insert 10. Now it has inserted 10 and it has started the recursion call for 10. Do you want to insert left of 10, right of 10? I will be like false for both. False, false. Now what happens is, false for this, nothing was called. False for this, nothing was called. Function is over. Which function is over? For the node number 10, the function is over. When function is over, it will be removed from the stack. What is the next function in line? 8. And where was it called? The 8 function. Where was we left? Where did we leave it? In 10. We called the right function, like right recursion call. And now it will come out of where? It will come out of here. Again, now it will be in line 46, 48. Function will be over. Means nothing else to do in 8. Remove it. Now it's coming out of 6. Left hand side of 6 it's coming out. Now we are in node is 6. We are in the 6th level call. It is coming out of here because this is what we called for 8. It's coming out of here. Now it's going to ask you, do you want to insert right of 6? Right of 6. Do you want to insert right of 6? Yes. True. Enter the value right of 6. I'm going to insert 14. Do you want to turn left of 14, right of 14? Now I'm inside 14. So it's doing the same thing for me. Insert left of 14, right of 14, false, false. I don't want to insert. False, false. So it's going to come out of here. So 6 is done. 14 is done. It is removed. Then it comes out of here. So 14 comes out of here because it was called here in the right hand side of 6. And after the function 6, both the calls are over. Function 6 also gets over. So this function 6 also gets over. Nothing else to do. It will also be removed from the stack. And when it is removed from the stack, from where it was called? It was called from the left hand side of 15. Left hand side from 15. Now it will come out of here in the function call. Do you want to insert right of 15? Sure. True. I want to insert right of 15. I want to insert 9. And I don't want to insert anything in 9. And my function is over. How? Nothing in 9. I inserted 9. Do you want to insert anything in 9? No, I don't. it removes, then it comes out of here, it comes out of the right side of 15 over here after inserting 9, and after that it's nothing left to call, so it's also function over. Where was the function called for the node value 15? Here it was called. It comes out of here, it comes out of here, program over. Okay, and one thing I want to mention here, I did a little typo. If node is equal to null, then I have to return it. I did not equal to, but what I can also do is I can check out the AI application and I can just ask it fix the null pointer error in this code, and I can just copy the code, paste it. So it's giving me the solution. It's saying that change not equal to double equal to. Thank you AI, really appreciate it. Equal to. Cool. Now what I can do is I can run this, and 5 and then 6, 15, true, 6, true 8, false, right of 8, true. I'll insert 10. I don't want to insert the left of 10. I don't want to insert the right of 10. Do I want to enter right of 6? Sure. I want to insert 14. Don't want to insert anything. You want to insert right of 15? True. I'll insert 9 and then false, false. Please display. Here you go. 15 is the root. It has two children, 6 and 9. Two children, 6 and 9 in the same level. You can see same level. 6 has 8 in the left, 14 on the right, and 8 has just 10 which is on the right over here. Nice. It is not really lovely. We can make it a little bit more clearer, but I think that should make sense a little bit. Okay, because you do know about the indents, right? If 6 has, because these two are on the same level, then this value will also be equal to the same. So if this has space 2, then whenever node dot left and node dot right are called in the same level, the space will be same. That's why it has same number of space from the left hand side. It's very easy, and we debugged it and we saw everything. So you can run it on pen and paper again to, if you want more assurance, but that's pretty much about it. Nice, very cool. All right, let's move forward and let's try to make it a little bit more prettier, the display function. Okay, so what I'm going to do is, let's say we have this tree. Okay, I'm going to create a new page, copy paste it, and let's say I'm just going to turn it like this. Okay, I'm going to turn it like this, and that's how I want to print my tree. So ideally what I would do is, let's say if we talk about the console, let's say I'm trying to print it in a nice way, okay, more prettier way. So this is my console log, then I'm printing it like this. Something like that. Make sense? So that's what we wanna, this is what we wanna do. So how are we going to do this? So you can see what is happening over here, that if I create another function, if I say public void pretty display, and what this is going to do is, this is going to call some other pretty display root, and it's going to call, let's say I'm going to add an indentation value, which is the spaces or the levels, let's say which level you are at, 0. Private void node int level, right. I'm not going to use the AI for now. Okay, so similar thing, if node is equal to null, I'm just going to say return. That's all right. what I want to do now is that I'm going to say go till the rightmost value that you can go to, because I'm printing right first. As you can see, imagine these as like the console lines. These are lines, right? So I have to go to the rightmost element first. I have to go to the rightmost element. So it's going to be like call the same function pretty display node dot write and level plus 1. As you're going to write, your level is increasing by 1. So level here will be equal to 1. Now again this will go to write, again this will go to write, this will have null, it will again go to write, it will have null, it will return. Now when it returns from here, here you have to check if level is not equal to 0, it means that I am not in the root. Okay, otherwise I can just say system.out.println node.value. But if it is not equal to 0, that means that I am not in the root right now, means I am at my node that I am in right now is some level down, which is in this case 1 level down. Hence I have to add that many spaces. So for example, let's say this is level 1, this is level 2 down, level equal to 2 down. So you have to have 2 spaces or something like that. So that's what I'm going to do. For int I is equal to 0, I is let's say less than level minus 1, I plus plus, this is just for indentation purpose. I'm just going to say print, let's say 2 tabs and also a dash like this. This is not going to be new line. After that, after you have printed your indentation, what I'm going to do is I'm going to print this line along with the number. So print ln the line along with the number. This line along with my node dot value. That sounds good. Otherwise just print the node dot value. Once all the right has been printed, right printed, yeah, sure, left, right nothing, left nothing, this left we have to write again, and then it will be come back in here. Okay, right is done, it is printed. Now go do the same thing for left. So now do the same thing for left. Very simple recursion, nothing major in this. Pretty display, run it, print ln, spelling mistake, no problem, run it. Let's start with something simple. 15, 9 and 6. Let's do that. 15, do you want to enter left of 15? True. I have entered 6. There you go. Makes sense. Initially there is no space, but now you can see now it looks like a tree. Let's try it again with some complex data. Let me try for this. 15, 6, true, 8, 10, 10 here, false, false. To enter right of 6 is 14. Oh, sorry. I had to do true, false. No problem. To insert right of, yeah, true. I have to insert 6. True. I have to insert 8. False. True. 10. False. False. Right of 6, yes. True. 14. False. False. Right of 15, 9. True. 9. False. False. Nice looking tree. Can you see? How cool is that? Very cool. Isn't this the same thing we have printed over here? This thing. Very nice. So how is it working? We know that the first line is going to be the rightmost element. Keep going to the right. Keep going to the right. It'll be like, okay, current node, it will be like, let's see how it will run. Current node is 15. It is going to go in 15. It's going to be like, okay, let's go in the right. Node.right is 9. Now it's in 9. Again, it will go in the right, which is null. So it will return from here. And now when it returns, where was it called? It was called here. So it will return from here. Level is going to be equal to 1 over here. So it's going to be like, if level is not equal to 0, that is correct. Add some space. Right now there will be no space because 0 is not less than 0. No space, and it is just going to print node.value. It's just going to print like this, 9. So it's just going to print 9. And after that it's going to come out of here and it's going to go with the node.left it's going to call, which is again null. So it will be returned from here. It will be returned from here. 9 will be removed. 9 will be removed. 9 will be removed where? From where? From here 9 will be removed. And here it will be now at 15, as you can see. And 15 level is 0. Level is 0 here. So level is 0, else it will just print 15. So it will just print 15 here, no space is added. After that it will call 15 of left with level plus 1. So 15 of left is 6, it will call 6 with level is equal to 0 plus 1, 1. 1 is over here. Okay, 0 plus 1, 1 is over here. And now it's going to be like, okay, 6. When it calls 6, again it will start from here. Go to right with level plus 1. 1 plus 1 is 2. Go to the right, 14. Then again call the right of this. So when it will start from here, the right of this is level plus 1. 2 plus 1, 3. Node dot right. So 3, but it is null. So it will just return from there. When it returns, it will come out of here, obviously, because it's called over here, the right. If level is not equal to 0, level is what? 2. Print some spaces. It will print some space. So it will print some space like this. And then it will say print node dot value, which is what? 14. It's going to print 14. And then it will be like, okay, I have printed it. Now it will go out. Node dot left, level plus 1. Left is nothing. It's empty. Okay, come out of here. Then it will come out of where? 14 will be over. And it will come out of 6's right, which is this line 72. So yeah, this line over here. Okay, 6 is right. So this is going to be removed from here. And when it comes out of this line, it is going to be like level not equal to 0. That is correct. Add some space. In this case, only one space is needed. So it's going to add in one space for you like this. And going to add in 6. Right? It's going to print 6. Then it's going to call the left of 6, which is 8 with level 2. It will again call right 10 with level 3. With more space, it's going to print 10 over here. You get the idea, you know. Then it will go back. It'll go back, and while it's going back, it will print 8 over here. And it's going back. And you have it like this. How simple is that? Very simple. We did the debugging and everything. It's very nice. So all I'm doing is I'm just trying to see the lastmost, and then as I'm going back, first I'm printing the right. As I'm going back, before I'm making the left call, I am printing the node, and before I'm printing the node, I'm printing right. That's it, because that's the structure we're following right over here. And I'm adding the space according to the level that we have. That's it. Very simple. Try it out on pen and paper. If you have done recursion, there should be no issue for you. It's very simple. We have done string problems and everything. It's very nice. Cool. The code you can find in the description below, so you can check it out. Okay, let's move forward. Okay, now let's talk about the main thing, which is binary search tree. So binary search tree is a type of a binary tree. So we'll talk about binary search tree. Insertion, deletion, and retrieval, log and time. Okay, because of what I showed you already, right? I showed you the tree and I did the log and everything on both sides. So we saw that maximum height is log n. Given that it's like a balanced tree. Balanced, we also talked about the height between any two should not exceed, height difference should not exceed 1. So how to keep a tree, let's say for the sake of this lecture, we will assume that every tree is balanced. Okay, means every tree has two nodes in which the height difference is like, you know, in two nodes, which is like more than two. Okay, so sorry, more than one. So it should be like the height should be less than equal to one in the adjacent, you know, like the nodes that you have. I'll show you in just a minute, and we'll also write a function to see that if a tree is balanced or not and things like that. But you get the idea. I already covered this in the previous like section of this video. I showed you like a really big tree and how that was like a linked list, which is not cool. So it has to be balanced. So let's see what do we mean by balanced tree. Let's see what do we mean by binary search tree. How is it log n and everything. So when we talk about balance, it basically means that the height of any two nodes that are like children, any two, it should be less than equal to 1. So this is a balanced tree. Okay. So we talk about the height of these two. What is the difference in height of these two? 0. Hence it is a balanced tree. What is the height difference between these two? Now, the nodes. These two height difference is 0. These two height difference is 1. Because the height of this is 1 more than the height of this. What is the difference of height now? The difference of height now is 2. This was initially 0, now 1, now 2. Not balanced. Height difference always has to be greater than equal to 1. Sorry, less than equal to 1. What am I saying? Height difference always has to be less than equal to 1 between any two nodes that are children. Okay, similar nodes. Any two nodes on the same level, in simple terms. Any two nodes on the same level should have the height difference less than equal to 1 only. What is the height difference between this one and this one? 0. What is the height difference between this one and this one? 1. Right? This will be the height of 0. This is height of 1. 1 minus 0 is 1. What is the height difference between this and this? I told you again, this is height, I talk about, let's say this is leaf, so it is 0, and this is what? 1, 2. This is 2, so height difference is 2. Not cool. Okay, that's basically what means by balance, non-balance. Now when we talk about binary search tree, it's simple. For every node, the left hand elements will be greater, right hand element, so left hand side element will be smaller, right hand side elements will be greater. So let's say you say insert 15. Okay, nothing is in the tree right now. I will insert 15 as the root node, and I'll be like, okay, insert 10. So you always start from the root node. Always, you know, you will start from root. So insert 10. Okay, is 10 smaller than 15 or greater than 15? It is smaller than 15, so it will go on left hand side or right hand side? Left hand side. Insert 5 into it. Okay, start again from the root node. Is 5 greater than 15 or less than 15? Less than 15, so it will go in the left hand side. Is 5, now again compare with 10. We go in the left hand side, 10. Now compare with 10. Is 5 less than 10 or greater than 10? It is less than 10, so it will go in the left hand side of 10. When we find a null value, we will add the item over there. So left hand side of 10 it will go. Left hand side of 10 is what? Null, add 5. Add 20, start from the root. Is 20 less than 15, greater than 15? Greater than 15. Add it on the right hand side. Right hand side is null, okay, add it. Null means there is an extra space, so we can add it. Add in something like, let's say we add in 12. Is 12 greater than 15, less than 15? Less than 15, so it will go on the left hand side. Now check for the left hand side. Is 12 greater than 10, less than 10? Greater than 10, check the right hand side. Right hand side is empty, okay. That's basically how you enter. Every single node, let's say for simplicity, what the node represents. You all know this. We will have int value we will have node left, we will have node right, and let's also store the height. Okay, let's also store the height, because just for simplicity purpose. Now you'll be like, Kunal, how do we calculate the height on our own? I will teach you that as well in the video when we will be doing questions of trees. Then I will teach you how to calculate the height also. So that's basically what we can have right now. And yeah, let's create an insert function. Let's see how we can insert in it and do all sorts of things. Okay, cool, let's code it. Okay, so here you can also see, if we talk about insertion, you're talking about, let's say I want to insert something like 3. So 3 less than 15, greater than 15, less than 15. So it will go over here, less than 10, greater than 10, less than 10, go over here. So you can see at every point of time, it will make comparisons like this, you know. It will make comparison with only one item at every level. It will not do like this. Let's take 2 items at this level comparison. Let's say I compare it like this, then I go like this, and then I go like this, and then I add. No, because in this case you can see it's comparing both the items on one level. It will never do that. It will only compare one item at every level. So it will compare only one item at every level. And for a nice tree that is balanced, what is the maximum height you can have? Total number of levels, log of n. Log of n, I already covered it, and that's why the maximum height is log of n, maximum comparison are log of n. That is why when you add, when you remove, and when you search, it is log of n. Clear? Okay, cool. So I'm going to, let's say, make another file. I'm going to say binary search tree.java. Okay, I'm going to say public class node we're having height, private node right, then my constructor this dot value is equal to value. Let's say we also create another function to get the value. You know, getter setter methods, we talked about those. Okay, that's my public class. Cool, no problem. For this one, we'll have also same thing as we did previously. Root node, constructor. All right, that makes sense. Very cool. Okay, now let's say we want to get a height. So if I say public, return the integer height of a particular node, what would that be? I will just say return node.height. If node is equal to null, height is -1. If there is no tree, then height is -1. Otherwise, just return node.height. Okay, similarly, I can say boolean is empty. When would it be empty? If the root is equal to null, then the tree is empty. Return root is equal to null, then tree is empty. Okay, now what all things that we can do here? Let's say we create the display one. If I'm just going to increase this font a little bit. So display, nope, get balance will make later. Public void display, and this is going to call display of root with, let's say, root node. I just add in a little text over here as well, and then I say private void display node string details. If node is equal to none, return. Otherwise, I will say details, like this is the, like for example, left child of this, right child of this. So details plus node dot value. So we will display the node value, but we will also display like what is the, what is the information about that. Okay, if we have node here, then node dot value node dot get value was the function we made, get value. Cool. And here I'm going to say that what am I going to do? I'm going to display the left and right. So display node.rel left, and the details are going to be equal to what? The details are going to be equal to that when I'm displaying the left, then I'm going to say this is left child of current node dot value. Okay. Similarly, node dot right child of node dot value. That's it. Pretty cool stuff, right? And we have to display the, let me just see how we can, no, that looks good. It'll make more sense when we have an insert function. So let's say we try to insert it. I think that's the more important one. Okay, so notice one thing over here, as we have seen that, Kunal, why is this log n? So for now, you know that the maximum height will be log n. Okay, whereas n is number of nodes, because we already talked about it. I showed you the mathematical information around that as well. Similar to binary search, you already know that. Okay, but if we talk about insertion, then let's say we want to insert 3. So it's going to compare this with 15. Is 3 less than 15 or greater than 15? Less than 15. Okay, go over here. Is 3 less than 10? Greater than 10? Less than 10. Okay, go over here. Is 3 less than 5? Greater than 5? Less than 5. Go over here. Okay, insert 3 over here. So you can see when it was inserting 3, it at every single level like this, level like this, level number 2 like this, level 0, level 1, level 2, at every single level it will only compare the item with only one node. It will not be like, okay, let's compare it like this, then let's compare 3 with these 2 items, then let's compare 3 with this item, and then we add it or whatever. No, never in a particular level it will compare 3 with 2 items, only one item per level, because that's how we're doing it. For every node we're trying left or right. Okay, that's either the question, either left or right, that's it, or at that position when it's null. So it will go either left or right. It will not move sideways in the level. It will only go down. That's why it will only make comparison one level on every, once on every level. So once on every level, then what are the total number of comparisons? Total number of levels. What are the total number of levels? Log n, where n is the number of nodes. How? I already covered that. I showed you, right? 2 raised to power h plus 1 minus 1 formula. Then we took total n is equal to 2 raised to power height plus 1 minus 1. How? We also showed that. The GP formula, I showed you that as well. So that's exactly what it is. Time complexity understood. Similarly, when you're finding the item, try to find 5. Okay, is root node equal to 5? No, it's not. Then check, is 5 less than 15, greater than 15? It's less than 15. Okay, then I know that 5 will be on the left hand side. Now search the left hand side 3. Is 5 less than 10, greater than 10? Less than 10. Okay, I know that the 5 will be in the left hand side of 10. There is no scenario in which 5 will be on the right hand side of 10, because it's binary search tree. And for the sake of the argument, for this log of an argument, I'm assuming that this is a balanced binary tree. Means difference between height of any two nodes in the same level should not be greater than 1. Very simple. Okay. So let's code this. Binary search tree.java. I wanna do it on my own. Okay, it's giving me all the AI stuff, but I can ignore that. I'll show you from scratch. Okay, so what we're going to do is I'm going to create a node type, public class node. It's going to have a value of int. Node left, right? And for the sake of this, like I also have it, I told you that we will take height as well as a property of the node. Okay, so we have height as well. Now the constructor, public node int value, node this dot value is equal to value. That's it. And let's say I have a get value as well, that gives me the return the value. Yeah, sure, no problem. Okay, so that's done. Now I will do some basic methods. Like first of all, I have to set my root. So private node root, and then I'm going to say public binary search tree. That's my constructor. Okay, no problem. Now what we're going to do is, let's say I calculate the height, public int height of a particular node. Just, if node is equal to null, it means what? Tree is empty, there is no tree, return -1. Empty tree, no height, otherwise just return node.height. No logic here, I'm just returning node.height. Similarly, I can do another thing, public boolean is empty. Is the tree empty or not? In that case, what do? If root is equal to null, then the tree is empty, otherwise it is not empty. Okay, very simple. Now we're going to try to insert something in it. So public void insert, I will just give it a value. So first thing I'm going to do is, what am I going to do? How am I going to insert it? I am going to say that insertion is a tricky part. It's not that tricky. Let's see how we can do it. So you all know that these things are connected with each other. Okay, so when I'm inserting in this, I want to insert 8, for example. Let's say I want to insert 8. So what I'm going to do is, I'm going to check whether 8 is smaller than 15, greater than 15. I'm just going to make that check. So forget about this. Let me just make a private function. I'm not going to write it down. Int value node. So I can say that if the value is less than node dot value, in that case node dot left is going to be equal to insert value comma node dot left. Insert value comma node dot left. So ideally what I'm going to say is that I have to make sure that, how do I say that? So let's say I simple example, okay, forget about the code, think of the logic. I'm saying 8 you have to insert, okay, I will say 8 is on the left hand side, okay, 8 is on the left hand side of this, okay, now 8 is on the right hand side of 5. So somehow I have to say that this node dot right is equal to 8. I have to say node dot right is equal to 8. So let's say I created 8 over here, and when this 8 is returned to the function call that was made over here, it should be set as node dot right. So whatever thing you are returning should be set as your answer. That is what I'm doing over here. Node dot left is set as an answer, whatever. So in reality, I'm returning node, not void. Okay. Now I can add in something like this. I can say, let's say if node is equal to null, I'm just going to say, if you reached a particular section, like, hey, check it for the right hand side of 5, then you're going to be like, hey, right hand side of null. Okay, then create 8 and return 8. So I'll create 8, return 8. Okay. Similarly, if the value is greater than this, then I will call write. Okay. And then we'll have to adjust the height as well, but that's later. Right? So what is happening over here? Let's see. We have the function call. Think about it. Initially we have 15 in it. 15. We have to insert 8. So it's going to check, is current node equal to null? No, it's not equal to null. It's actually 15. It's the root node. Is the value less than 15? Yes, it is. Okay. Then node dot left is equal to whatever you are going to return from here. So 15 dot left is going to be equal to whatever you return from here. Now there are two scenarios. Either this will be empty or not empty. If it is not empty, then it will not change. It will remain 10 only. I will show you when debugging. So it's going to be like, okay, node dot left, 15 dot left is going to be equal to whatever is returned from here. We are calling this in node dot left, so 10 will go over here. Now it's going to be like, okay, if is 10 equal to null, 10 is not equal to null, then check, is 8 less than 10 or greater than 10? Less than 10. Then okay, again 10 dot left is going to be equal to whatever you return, but first call it with the left of 10, which is again 5. And then it's going to be like, okay, calculate, is 8 less than 5? No, it's not. Then okay, check this one, is 8 greater than 5? Yes, it is. Then okay, 5 dot right is going to be equal to whatever answer you get. Okay, I'm going to call it with null because 5 dot right is equal to null. Okay, I'm going to call it with 5 dot right. Okay, so now it's going to null. Is current node equal to null? Yes. Create a new node based on the value. The value is what you want to insert, so it creates a new node over here, and then it will return this node from here. So here this node that is returned will be equal to what? 8, and that is set to what? 5 dot right. So now automatically 5 dot right is equal to 8. Now you get out of here. Now when you're getting out of here, you are out of the 5 function call. You are out of the 5 function call. So 10 dot left was equal to something that was called. So 5 should be returned because we don't want to change what is already assigned to the tree. You get my point? 5 is already assigned to 10. Then I don't have to change that, right? I can just say, okay, return whatever this is. Return whatever current node we have. Do you understand? Think so? Nice? Makes sense? Okay. So that's basically the idea. But now since you have added one more thing over here, the height of every single node has changed. Now it's traversing back. So while you do this, you have to say node dot height is equal to maximum height of left and right plus 1, because you have just added one more element. So new height is going to be equal to what? Whatever the old height was plus 1. Maximum of this and this plus 1. New height for 10 will be equal to what? Maximum of the left hand side and right hand side plus 1. Plus 1, which is for equal to, like for this thing that we have, like this edge is one node. So whatever the height is for these two, let's say height for the left node is what? 1. Right node is what? 0. This will be equal to what? 1 and 0, which is the maximum. 1 is maximum, plus 1, 2. Correct. Okay. And here what is going to happen now? See, it's very simple. It's going to return 5, and 5 will be returned from where? From where it was called. So when you're saying node.left is equal to function call, you are not saying like, oh Kunal, node.left already has something attached to it. Is it not the case that it will be changed? No, it won't be changed, because there are only two cases. If it is null, a new node will be created, it will be added. Otherwise, the same node will be returned. So you are saying node.left is equal to insert something with other node.left. That same node is being returned over here. Okay, so it will be like, okay, 10.left is going to be equal to something. If there's already something attached to it, don't worry, that same thing is being returned, so no change will be made. But if something is not attached to it, then we will add it, create a new node, and then we will return it, and then it will be attached. So 5 will be returned from here, it was called from left. So node.left is going to be equal to 5, which is no change. 5 is removed. Now when 5 is removed, it's going to call the right hand side, and it's going to be like, no value available over here. We are not going to go in the right hand side, because at every single level it is going to only compare once, as I mentioned in the just recently. Then it is going to update the node.height. So height for 10 will be updated, maximum of this and this, which is 1 plus 1. So height now here will be 2. Height is updated to 2. It will come out of here, and now it will be out over here for 10. So 10 will be removed from the left hand side of this function call for 15. We are in 15 right now, 10 will be removed from here. So 15.left will be equal to 10. No change, because node is returned. 10 is returned, no change. So 15.left will again be assigned to 10, which is no change. And then height will be updated. For 15 it will be 3, because this is 1, 2, 3 and 1, so maximum is 3. So 1, 2. So maximum of what? Maximum of 2 and this height is 0. 2 and 0 is height what? Maximum is what? 2. Because it's just a property of the class. As you can see, property over here. This thing. So you don't have to traverse again. We are storing the property in every node. So we'll just take the property. 2 or 0, which is greater? 2 is greater. Okay, new height is equal to 2 plus 1. Plus 1 for this line, this edge. New height is 3. New height is 3. After this it will return 15. Okay, 15 will be returned from where it was called. Where was it called? It was called over here. And it's saying root is going to be equal to 15. So in the end, we know in the end root is returned, so we just assigned it to root again. Okay, so the doubt you will have over here is, I know where the doubt you will be having. The doubt you will be having is, Kunal, you're saying node.left is equal to insert, but what if it changes the node.left that we are assigning? It's not going to change it, because it's returning the same thing. Node.left is equal to something. If that something is not null over here, then it will return the same thing. Node.left, 15.left is equal to 10. I know that it is not empty. Don't worry, in the future it will return 10 only. Okay, because it is returning the node only. I hope that made sense. Right? Cool. Okay, so since now we have the height over here, I can also check if the tree is balanced or not. So I can say that public boolean balanced, don't have to pass a node. I can just say return balanced. Is the root balanced or not? For this I'm going to create a private boolean balanced node. To check if it is balanced, I can say if node is equal to null, yeah, no true. Null means it's empty, so tree is balanced because there is no tree. Otherwise I'm going to say return math.abstract. I'm going to say height of node.left minus the height of node.right should be less than equal to 1. That is one case. The height should be less than equal to 1 for these two. Okay, that's fine. But there might be a case that we also have to check for the subtree, right? For this node, you're checking that the children are at good heights. Okay, that's fine. But you have to check for this separate tree also. Now check the same thing for the left tree and the right tree. And check the same tree for the left tree and the right tree. This is the code. Simple. So here it's checking. Let me just write down the heights. Let's write down the heights. 0, 1, 2, 0, 0, 3. So it's checking. Difference between the height of these two. 2 minus 0 is equal to what? 2. This is not a balanced tree. Not a balanced tree. Let's say for the sake of the argument, I add in a tree over here. A node over here. 4, 0, now this is 1. So I start from here, I say okay, left and right, 2 minus 1 is 1, yeah, that's fine. So this level is balanced, but I have to check it for all the levels. Now let me check for this one. So this one is saying 10 should be balanced as well. 1 minus 0 should be equal to less than equal to 1. That is correct. And then it's going to check for the left again. 8. So 8 is saying that it's null. Let me just write the whole function stack. Okay. Okay, cool. We're starting from 15. Okay. 15 added over here. No problem. Now, is node equal to null? No, it's not. Node is not equal to null. Return the height difference between left and right should be less than equal to 1. So height difference between 2 and 1 is less than equal to 1. Yes, that is true. And balanced node dot left. Now it's calling left. Now is 10 equal to null? No, it's not. Now check the left and right. So this is 1, this is 0, that is correct. Okay, now go again in the left. Check again for left and right. Height is 5 is equal to null. 5 is not equal to null. Okay, height of node dot left, height of node dot right. So height of node dot left is equal to what? There is no node dot left, so it's just going to return true from here. And node dot right is 0. That's fine. Balanced of node dot left, which is if I check my height function, if node is equal to null, it is returning -1. So this will return -1 and this will return 0, which is 1, so it's fine. And then it's going to be like, okay, balanced node dot left, 5 dot left, which is null, so it will return true. So here you will get true. Now node dot right, which is 8 again, null, it's going to return nothing. It's just like null over here. Node dot right and nothing. So here it will have height is node dot right. So here it's going to be like so for 8 it's going to be like when it goes in when it goes in node dot left minus node dot right. So node dot left is going to be equal to give me what? It's null, so it will give -1, which is 0, so it will say true. Okay, no problem. And then it will go for node dot left, node dot right. So node dot left will return true because it's null. Base condition null, true, it will return true. This will return true. So true and true and true will return true. This will return true. Now 5 is out of the stack. Now 12 will go inside the stack. When 12 goes inside the stack, it will be like height of node dot left, node dot right, 12 dot left, 12 dot right, minus minus 1, minus 1, minus 1, 0. So that is true. And balance node dot left, balance node dot right. Node dot left of 12 is 0, right is also 0, mean null, sorry. So it will return true. True, 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 it is going to return true. 10 will come out of here. It is empty, okay. 12 came out, 10 came out. Now 15, similarly. Cool. Make sense? Right? Okay, so that was cool. And now let's talk about, let's display it. I'm going to pass in a message. So the idea is that it is going to display it is going to display the node, but it will also display the information about that node. So if node is equal to null, I will just say return. Don't display anything, just return. Otherwise, I'm going to say print details plus node dot value. Okay, no problem. So details right now are root node and node dot value. So when you start, initially 15 will be inside. So is 15 equal to null? No, it will print root node 15. That is what it will print. Okay, after that it has to go in the left hand side, and the left hand side message with this node will be, if it goes 10 over here, the message that I'm sending will 10 will be left of 15. Okay, similarly let's run this and then we'll see how it works. Created the balanced, and insert is also created. So let's say I want to insert multiple items. I don't want to be able to, so I can say public void populate nums, and I'm going to say for int I is equal to 0, I is less than nums dot length I plus plus. I'm just going to say insert. So I'm just saying that I'm giving you an array and run the insert function on that multiple times. It's just very, so that I don't have to write again and again in the command line, you know. Okay, let's run this. Binary tree is equal to new binary search tree dot insert. Not insert, tree dot populate new integer. I don't want to add a, you can say int nums is equal to this, and tree dot insert nums random numbers, tree dot populate nums, and then I can say tree dot display. Let's run this. Obviously line 35. Return node, that's okay. Incompatible BST.node cannot be converted to int. Oh, value is first, node is second. Make sense? And then tree.display, line 13. Typo? Silly mistakes, never mind. Okay, so we made, okay, so root node is 5. Let's see how it was created. Root node is 5. 5 inserted. Okay, now 2 should be go on the left hand of 5. Left side of 5 should be equal to 2. Left side of 5 is equal to 2. Now 7. 7 should be the right of 5. Right child of 5 should be 7. That is correct. After that 1 is inserted. So 1 should be what? It should go over here. Then it should go over here. 1 should be here. Left of 2 should be 1. Left child of 2 should be 1. Left child of 2 is 1. So displaying it twice. Let me see what's wrong. I added it by mistake twice. No problem. Right? That looks much better. Left child 2, right child of 2 is 4. I want to insert 4. 4 will be like less than 5, greater than 2. Yeah. Right child is 4 and so on and so forth. Makes sense? Sounds good. You can also use the same method we made previously to see the tree, the pretty display one, but this is just, I wanted to teach you something different. So I hope the insertion thing is clear. I've talked about insertion one. I talked about the, I showed you how to do it with the 8 example. I showed you the running of the code as well and everything. So I hope it should be clear to you. One problem with this thing is, do you know the problem? You know the problem. If this array is sorted, then it will create a tree like this. That will be very bad. So how do you fix that? You can use balancing trees, but let's say specifically if you want to do it for sorted arrays, then we can do something like that. Let's see. Okay, so let's say you're given a sorted array 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 or whatever. Okay, so what you're going to do is you want to create a binary search tree, but you have to make sure it's not like skewed, just one line. So a better way to do this is self-balancing binary tree, where it balances automatically, AVL and something. That is next lecture. Okay, we'll talk about it and then. But let's say you're specifically given a use case that it is a sorted array. In that case, you can just take the middle element and then divide it into 2 parts. Middle element divided into 2 parts. For example, 1, 2, 3, 4, 2, 3. So you take the middle element 5, add it. Simple. Then you call the left hand side and the right hand side. As simple as that. It's very easy. Populate the left hand side and the right hand side. When you talk about left hand side, again take the middle. Let's say it's 2. Add 2 over here. Call again the left hand side and the right hand side. Left hand side is only 1. Okay. Add 1. Right hand side was 3 and 4. Okay. Add 3. And then 4, which will go over here. For this, again take the middle element 8, Now this will be one side, this will be another side. 6 and 7, take the middle element, let's say it's 6. Again recursion, and then 7 will be on the right hand side, like this. Okay, 9, 10, take again 9, 10. That's basically how you can do it. Okay, take the middle element, add it as the current node, then split it. Just insert it. You don't even have to maintain pointers over here. You can use the insert method that we used. Take the element number 5, insert it. Then divide it into 2 parts. Then again take the middle element, insert it. Take the middle element, insert it. So it's very simple. If I go over here in my populate one, then I can just say let's say this is a sorted array. Then I can say no, I don't have to do root. I don't have to do that. I can just say populate sorted and nums start from 0, end with nums dot length. That's it. Private void populate sorted nums int start int end. Now base condition, if start is greater than equal to end, I will just say return. Otherwise I will just calculate my mid. Int mid is equal to start plus end by 2. Then I will say call the insert function. Just insert normally nums of mid. The middle element, just insert it. After that, call the same function call for left and right. Populate with sorted with left and right. Populate with sorted. Nums left is what? Left is what? If this was start, this was mid, this is end. So left will be equal to start and end will be equal to mid. Start and similarly if you want to call it for right, it will be what? Right array will be mid plus 1 and end. Done. That's it. That is it. As simple as that. So you can try it out yourself. You have this array and you want to insert stuff in it. Not in it, but you can create a tree with it, you know. This is only a case for sorted arrays. In general, we'll be using self-balancing binary tree. So it will be like, okay, get the middle element, whatever that might be, 5, insert it. Okay, normally I inserted it. Go in the left hand side, right hand side. Now it's gonna go in the left hand side first. It's gonna be again like take the middle element, insert it, then go again on the left hand side. Only one element is remaining, insert it, then again go on the left hand side or right hand side. Now it's going to be like start is greater than equal to end, so it will just return and then it will be like, okay, you have returned, now go in the right hand side. Now it will go in the right hand side. You'll be like, okay, I'm in the right hand side, I will again take the middle. What is middle? Middle is 3, insert it. Then go in the left hand side. Left hand side we have nothing. Then go in the right hand side. Right hand side we have 4. Okay, take the middle of 4, is 4 only, insert it, insert it. Similarly, you will fill this one as well. Easy, very simple, right? Sounds good. What is the time complexity? It's very simple. You are inserting n elements and you're calling the insert function n times, n log n. Okay, because you're inserting it n times and every operation takes log n time. So n log n. Very simple. can run it and do all sorts of things. All right, now let's talk about one of the most important topics, very important. And we're talking about the topic right now, but we'll do some questions when we do the questions video. That's how I like to structure my video topics. If you have seen previous videos, one video will be on the theory, the next video will be on the questions. So like binary search, we did a theory of binary search video, and the next video we did was on interview problems or questions on binary search. Same thing we'll do in trees. Right now I'm doing tree. The next video is going to be on advanced theory of trees like AVL, self-balancing trees basically. And then we'll do a video on trees interview questions like Google, Facebook, Amazon, Microsoft, and all these other big tech companies, Apple and stuff like that. What sort of questions they ask, how to think, what all theory we have learned, how to apply that, which algorithm to apply and stuff like that. So right now we're going to learn about some tree algorithms. So let's learn about some of the traversal methods. This is very important topic. I'll also teach you when to use which method and what are the benefits and like what are the use cases of each of these. So let's start with three of these first. The first one is called pre-order traversal. If you have your node over here as like this, you have a left child, you have a right child, then pre-order traversal looks something like this. Pre-order looks like node left, right. Node first will be displayed, then left will be displayed, then right will be displayed. An example, if I have something like 10, 20, 12, 15, 13. Then if I talk about pre-order traversal, start from node. So every time is going to be like whatever node I am currently, I will display that node first because that is what the traversal order says. Let's say I start from here. I am starting from 10, I will display 10. Then I will go in left. I am in left now. I will first display left, whatever node I am in currently. I will first display that. Then I will go again to where I am going. Where am I going first? After you display the node, you're going to the left first, okay? I'm going to the left first. I'm first going to display this. Then I'm again going to go left. It's null. Okay, after that I'm going to go to right. Okay, it's null. Okay, come back. Now I'm coming back from 20. So I'm coming back from 20. It will now be like, okay, 20 left is displayed. After that 20 right will be displayed. 13. 10, 20, 15, 13. 10, 20, 15, 13. And after that, it's going to be like, okay, this is done. 10 left is all printed. After that, 10 right will be printed. 10 right is printed, which is just 12. So you can see node 1 is printed first. Any node is printed first. Then its left is printed first. Then its right is printed. That is pre-order traversal. This is pre-order traversal. Okay, now let's talk about some important points like when do we use pre-order traversal. So when you have to create a copy of your binary tree or when you have to evaluate some expressions, like you know the example I gave you for mathematical expressions used for evaluating math expressions or making a copy. Okay, right? And when you have like a string or an array and you want to convert that into a binary tree or do vice versa, like serialize it. In serialization also it helps. Okay, that is pre-order traversal. Very simple. I showed you example also. Moving forward. Number two we have over here is in order traversal. Node left, right. In order you can imagine from inside. So first it will display left, then node, then right. Okay, so let's say we have the tree again, which is like 10, 20, 12. First I will display left, then node, then right. So I'm at my current node right now. Will I display this? No, I will not display this. I will go to left first. I'm going to left. Will I display this? No, it says go to left first. When you say n, then only you display the node. It's saying go to left first. Okay, go to left. Will I display 15? No, I will go to left first. Left is nothing. Okay, returned. Now I will display 15. Now what will it do? Go to right. Right is nothing. Okay, return. Then I return. Okay, now for 20, left is displayed. What would I do? Go to right? No. Left is displayed. Display the current node 20. Then go to right 13. 13 left and right and nothing. 13 is displayed. Okay, similarly now left hand side of 10 is covered. So left hand side is covered. Now display 10. After that go to right. Now I'll go to right 12, nothing is there, so 12 is displayed. So node left right. For one node the left will be displayed first, then the node will be displayed, then the right will be displayed. Same thing you can figure out for the each and every single like sub of these displays as well. So this is one part of the display. Here also you can see that if I talk about this one, left is displayed first, then node is displayed, then right is displayed. So again recursion. Okay, make sense? That is in order traversal. 15, 20, 13, 10, 12. In order traversal. So how do we do this? What is happening over here? Actually, what I did was I did not take like a binary search tree example. Okay, I just took an example of a normal tree. This is not a binary search tree, right? But the use case is that in binary search tree, if you apply in order traversal, then you can visit the nodes of a binary search tree in sorted manner. Visit node in sorted manner. Okay, so you can print the node in sorted manner. Let's say if we take an example of that only, let's say I create a binary search tree. So we know that the leftmost item that we will have, that will be the smallest one, because we know for every tree, left hand is the smallest, right hand is the biggest. So obviously the leftmost will be the smallest one. So if I'm trying to print this, I'm first here. Will I print this? No, I will go to the left. Will I print this? No, I will go to the left. Will I print this? No, I will go to the left. Will I print this? No, I will go to the left. Left is nothing, so print this. 2 is printed. Right is nothing. And then I go back. Left side is printed of 3. Yes. So recursion call will be back. Now before calling node.right, I will print 3. Then I will call node.right, nothing. Okay. Go back. 5.left is completely printed. Print 5. Go to 5.right. 5.right is 8. Print it. 8 will come back. 10.left is completely printed. Yes. These all are completely printed. Then print 10. Go to right. Is this sorted or not? So what's the use case of in order traversal? In a binary search tree, if you want sorted order, use in order traversal. Third, post order. I'm telling the use cases also. Post order traversal. Post order traversal A, left, right. First print left, then print right, then print the node. Okay. First print left, then print right, then print the node. Right? If I take the same example, I am at this node. Will I print this node? No, I will go to the left. Will I print this node? No, I will go to the left. Will I print this node? No, I will go to the left. Left is empty, return. Now when I'm returning, will I print this? No, I will not. I will go to right. Right is null. Now I'm returning, now I'll print it. Now node.left, when it was called from 20, it is printed. Now when it returns, do I print 20 or do I call node.write? I will call node.write. 13 will be called, it will see there's nothing, then it will be printed. Both left and right of 20 are printed. Now I will print 20. Similarly, after this, left hand side of 10 is printed. You can see all the 3 elements on the left hand side of 10 are printed. Will I print 10? No, I will not print 10. It says go to right first. Okay, 12 printed. Then when both the left and right of 10 are printed, then I will print 10. Post order traversal. First print left, then print right, then print the node. And this boxes that I'm making will also hold true for subtrees, for this tree also. As you can see, first print left, then print right, then print the node. Post order traversal. Simple recursion, right? Now, when do we use post order? So post order traversal we use, I'm giving you the reasons also, when things are asked you. So when you need to, let's say, delete a binary tree, like delete from binary tree, then you use post order, because that is very important. How can you delete the node if it has left and right children? Can you do that? No. Can you delete this 20 from here? Absolutely not. Because what will happen to 15 and 13? Hence, take care of the children first, then worry about the node. That is why when you delete something, that is when you use post order, it makes sense also. Or when you perform bottom-up calculation, like calculating the height, then also you use post order. Or when you calculate diameter of a tree or whatever. We'll do these questions in the questions video, okay? Okay? Sounds good? So when you delete stuff and everything, that's when it's used. Okay, there are two more, the most important topics in trees, and this is where the questions will be asked to you in the interview. Two most important topics. BFS and DFS, or BFT or DFT. What is this? Breadth first search, depth first search, breadth first traversal, depth first traversal. Breadth means like this, breadth, depth. Traversing a tree like this or traversing a tree like this. This is the most important topics. 99% when you get a tree question, it will be BFS or DFS. Or BFT or DFT. One is just traversal, like traversing. One is searching, as for searching. Now, this will do is separate video. This topic is so important that I will make a separate video on this. I can't cover this topic in this video because then this video itself will be 8 hours long. 8 hours long. I can't do that right now because I have to make sure that I separate the theory with the questions, because that's what I have been doing since all the videos. Like linked list, I did theory, then I did another video on questions. Binary search theory, another video on questions. Recursion theory, another video on questions. It makes it easy to format and for you to learn also. Separate video on this. The more views I get, the more likes I get, the more comments I get, the more it will motivate me to create such videos. I am really serious about completing this bootcamp ASAP now, because I want to teach machine learning and web development and the open source course and the remote work academy. I have so many things planned for the community. And my travels have stopped right now, and I have a 4-day work week where I do full-time work. So in the next 2 months, at least a few weeks, DSA bootcamp will be finished. It will be completed. And the more likes I get, the more views I get, the more shout outs you give on socials. So what you can do is you can maybe take a screenshot of this and you can share it on socials, Twitter with hashtag DSA with Kunal, how excited you are to learn this video. and give all the positive feedback, because we are not charging any money from this. I want to make sure that such free resources reach every single person. No paid course like this is barely going to teach you in so much detail that I am teaching you and giving you so much, time and everything. So I should be just comment as well what you liked, and if you think it's such an incredible video, comment it. You have been requesting DSA, DSA, DSA. My brain got like, tired how much you are requesting. So now that I'm finally making it, I want to see the enthusiasm, okay? Because that will help in getting these videos in the hands of people who don't know about the course right now. And you and me together, we can make this free education thing a reality. Okay, so this I will cover in separate videos, but let's code in order, pre-order, post-order. Let's code this. Okay, let's try and coding this. So yeah, I want to see your tweets, your comments, your likes and screenshots and everything. Code will be found in the description below. And assignments also you can find in the GitHub repository. Okay, so I showed you the entire like how it runs and everything, but still we can code it, binary tree, and I can add it over here. I can say public void pre-order traversal starts from the root, and it's going to be node. If node is equal to null, then just return. Yeah, that's fine. Otherwise I'm going to say print. What is pre-order? Pre-order is print the node, then go to left, then go to right. Print the node, it will show me some. Print the node, then go to left, then go to right. How cool is that? Okay, you can add in a breakpoint like this, and you can go and debug it. Play and debug. Right? Like this, how it's going inside, next step, call stack, everything you can see, value of I and everything. But anyway, I'm going to show you with like manual debugging, as I can do that. So here what's happening is pre-order traversal. Okay, so it's going to start from here 10. It's going to be like, hey, I'm in 10. Is 10 equal to null? No, it's not. Okay, print 10, go to left, go to right. Print 10, now go to node.left. Now in the function call, I printed 10, now I have 20. It will say, is 20 null? No, it's not. Print 20. It will print 20. Then it will be like, okay, now next function call, we have 15 over here, 15 node. Print 15, go to left. Left is null, it will just return. Then okay, now what? It returns from here, now print right. Print right. Right is also null, okay. Now all of these things are done, it will come out of the function called pre-order. Function is call is over, means 15 is out of the stack. 15 came out from here. Now I am in 20, so it will say node.write. Node.write is 13, it will add 13 over here. Okay, so it's going to be like, now I'm in 13. Is 13 equal to null? No, it's not. Print 13, it will print 13, then it will go left and right. Left and right both are null. After that it will come out. When it comes out, 13 will be out, and now I am in function called 20. Function called 20, it will come out of here. Now function called 20 is over, so function of 20 will be out, and it will come out from where it was called, and it was called from function called 10. Function called 10 left hand side. Here is where 20 was called, so it will come out of here, and it will say 10.write. 10.write is 12, so 12 will go here. And it will say, is 12 equal to null? No, it's not. Print 12. It will print 12. Go to left and right. Left, nothing. Right, nothing. Come out. 12 is out. 12 is out. 10 is remaining. Now I'm in 10. It will come out of here in function call 10. Then there is nothing. Function call over. 10 is over. 10 will come out. That's it. Easy. Simple. Okay, every number being printed 1, if there are total n numbers, then O of n. Okay, very simple. Similarly, I can say in order paste in order traversal and post order traversal. So I'll just copy paste. In order traversal, what happens in order? Left first, then node, then right. So in order, left first, then node and right. In post order, left, right, then node. Left, right, then node. I believe you can run it yourself. It's very easy, you know. I ran it. It was pretty straightforward. All the code can be found in the description below. Same way as I did previously. Same thing, same stuff. I just ran. You already know recursion, so this should be simple to you. All right, sounds good. Nice. So that was pretty much about it. That was it. All right, what I want you to do now is, if you haven't already, take a screenshot, share it on socials, use hashtag DSA with Kunal, tag me, show the excitement, how excited you are. Assignments, code, and all the repositories, all the code that I have run can be found in the description below. You can directly run it on your browser as well. Questions and everything found in the description below on the GitHub repository, assignments and everything. Next videos we'll learn advanced data structures for trees, like self-balancing binary trees, and then we'll do a nice 4 to 5 to 6 hour long video, or like a really big video like I did for binary search, that would be just on questions, and not just questions, how to think, what intuition to build, how to use the type of algorithms and the type of data entries, the popular questions, and just any question that will be given to you, you'll be able to do it. But the faster you share, the faster you comment down below and like and share on your social media platforms and tag me, the faster I'll be able to make these videos. I promise you, you will see yourself by next week. By next week, you'll see all these videos that I'm mentioning that will be coming out. So yeah, that's pretty much about it. Thanks a lot for watching. Make sure you do the action items, which is taking screenshots, sharing hashtag DSA with Kunal, and sharing with your friends. No need to buy any paid courses. I'll teach you data structures incredibly well, including web dev and machine learning and stuff. So yeah, let's do this. Let's do what VMake Devs has been all about. Thanks a lot for watching. I'll see you in the next one. Comment down below if you have any questions. But yeah, one thing I want to do, if you're watching this video, comment. Everyone comment, because if you comment, these videos will be discovered by other people, and share it on socials. Don't want your money. All I want is comment, like, and for you to share on socials. Thanks for watching. Make sure you do that. I'll see you in the next one. Have a great day.